Light does not merely illuminate the universe, it defines it. There exists a speed beyond which nothing can travel. No signal, no particle, no influence of cause upon effect. It is the ultimate limit of reality, the pace at which the universe allows events to occur, a number so fundamental that modern physics uses it to bind space and time into a single structure. That number is 299,792,458. For generations, it has lived quietly inside equations and laboratories, expressed in symbols rather than stone. It is the speed of light in a vacuum, the cosmic limit written into the laws of nature themselves. And then, without explanation, the same sequence of numbers appears again, not in mathematics, not in physics, but etched into the geography of the Earth. 29.9792458 degrees north. At first, the resemblance feels incidental, even uncomfortable, the kind of numerical echo the mind is trained to dismiss. But as the view pulls back, those coordinates resolve into a familiar silhouette. The Giza Plateau, a place already known to challenge assumptions about ancient knowledge. In a previous exploration, this same monument revealed a quiet and unsettling relationship with pure geometry, a stone expression of mathematical order long before such ideas were formally defined. This time, the implication is different. Geometry describes shape. This number defines reality itself. No declaration is made, and no conclusion is forced. The numbers are simply allowed to coexist, side by side, separated by millennia, yet bound by precision. And so the question remains, suspended in silence. Why does a monument built 4,500 years ago rest on a number that modern science uses to describe the ultimate speed of the universe? For most of human history, numbers were silent companions. They measured fields, counted seasons, tracked the movement of stars, and faded quietly into the background of daily survival. They were tools, not messages. Means, not meaning. Yet on rare occasions, numbers refuse to remain silent. They intrude, they repeat, they align in ways that feel less like accounting and more like intent. The Great Pyramid of Giza has long been one of those intrusions. Long before modern science, long before equations described the universe in symbols, this monument stood on the edge of the desert, already ancient by the time classical Greece began asking its first philosophical questions. Egypt itself, by the reign of Khufu, was not a primitive culture experimenting blindly with stone. It was the product of centuries of consolidation, administration, astronomy, agriculture, and ritual precision. The Nile flooded with clockwork regularity. The stars rose and set with dependable rhythm. Order, or ma'at as the Egyptians called it, was not an abstraction. It was the principle that sustained the cosmos. Within that worldview, measurement mattered, not loosely, not symbolically, but precisely. The Great Pyramid was built during Egypt's 4th dynasty, around 2600 BCE. Its construction required logistical coordination on a scale unmatched until the modern era. Millions of limestone blocks, surveyed foundations leveled to within centimeters across hundreds of meters, cardinal alignment so accurate that even today, with satellite technology, it is difficult to improve upon. These are not disputed facts. They are accepted by mainstream archaeology. The debate has never been about whether the builders were skilled. It has been about how far that skill extended. And now, a number forces itself back into the conversation. 29.9792458 degrees north. This is not an interpretive value. It is not symbolic. It is the measured geographic latitude of the Great Pyramid's apex. To understand why this matters, one must first understand what latitude actually is. Latitude is not an abstract grid imposed arbitrarily on Earth. It is an astronomical measurement. It describes the angle between the horizon and the celestial pole, determined by the rotation of the planet itself. Stand at the equator, and the pole star sits on the horizon. Stand at the North Pole, and it is directly overhead. Everywhere in between, latitude corresponds directly to the sky. Long before compasses, long before satellites, latitude could be determined by observing stars. The height of circumpolar stars above the horizon reveals position on the globe. This was known to ancient navigators, astronomers, and surveyors. It does not require modern instruments. It requires patience, observation, and a stable sky. The ancient Egyptians had all three. They tracked the heliacal rising of Sirius to predict the Nile floods. They aligned temples and pyramids with stellar risings and settings. They oriented the Great Pyramid not toward magnetic north, which wanders, but toward true north, defined by the stars themselves. This is not speculation. It is supported by alignment studies and astronomical reconstructions conducted over decades. Latitude, then, was not unknowable. But modern latitude is expressed in decimal degrees, a base 10 subdivision of a circle. This is where skepticism enters, and rightly so. The ancient Egyptians did not use decimal notation. Their mathematics was based on fractions. They did not divide circles into 360 degrees in the way inherited from Babylonian astronomy. They did not speak in seconds or milliseconds of arc. And they certainly did not use meters, seconds, or any modern physical units. So how could a pyramid encode a number that appears meaningful only when expressed in a modern coordinate system? This objection is the strongest argument against intentionality, and it cannot be dismissed lightly. Yet it is not the end of the story, because while units change, ratios do not. A ratio is dimensionless. It exists independently of the measuring stick used to reveal it. The ratio between the circumference of a circle and its diameter is pi, whether the circle is measured in cubits, meters, or miles. Pi does not belong to any culture. It belongs to geometry itself. When earlier explorations revealed that the Great Pyramid's proportions approximate pi with striking accuracy, the argument was not that the Egyptians knew the Greek symbol. It was that they understood the relationship. This distinction matters. Latitude at its core is an angle. An angle is a ratio between arc length and radius. It is dimensionless. Decimal degrees are merely one way of expressing it, just as meters per second are one way of expressing speed. When modern science writes the speed of light as 299,792,458 meters per second, it is choosing a language, not creating the value. The constant exists regardless of how it is written. Here is where the coincidence begins to feel less comfortable. The latitude of the Great Pyramid is not approximately 29.98 degrees. It is not rounded. It does not drift, depending on measurement. When expressed to sufficient precision, it aligns exactly with the speed of light to 7 decimal places. Not 6, not 5, 7. To put that precision into perspective, shifting the pyramid's location by less than a meter would alter the 7th decimal place. Geological surveys confirm that the pyramid sits exactly where it appears to sit. This is not an artifact of modern mapping error. Still, skepticism remains justified. Numbers can align by chance. The human mind is skilled at finding patterns, even where none exist. Statisticians warn against apophenia, the tendency to perceive meaning in random data. In a world saturated with numbers, some will inevitably resemble others. But context matters. The Great Pyramid is not a random structure at a random location. It is a monument already saturated with mathematical relationships. Its perimeter-to-height ratio approximates a fundamental constant. Its orientation aligns with celestial motion. Its dimensions scale to planetary measures in ways that have been debated, criticized, and yet never fully dismissed. When a structure with no known parallels in precision produces yet another numerical convergence, coincidence begins to feel less like an explanation and more like an evasion. History deepens the tension rather than resolving it. Egyptian civilization did not emerge suddenly. It inherited knowledge from earlier periods, some of which are archaeologically faint but culturally persistent. Sacred geometry, cosmological symbolism, and observational astronomy were not separated disciplines. They were integrated expressions of how the Egyptians understood existence. The sky was not metaphorical. It was a clock, a map, and a divine text. In such a worldview, building was not merely functional, it was cosmological. Temples and monuments were meant to anchor heaven to earth, to reflect eternal order in physical form. Measurement was not neutral, it was sacred. Yet none of this proves intentional encoding of a physical constant. And that is precisely why this moment matters. If the match between latitude and the speed of light is meaningless, it is extraordinarily precise for no reason. If it is meaningful, then it implies a mode of understanding that does not align neatly with modern historical categories. Either possibility is unsettling. And so curiosity awakens, not as belief, but as obligation. Because once a number refuses to be silent, the only honest response is to listen further. And the question presses harder now, no longer whispered, but waiting. If this is a coincidence, why does it feel engineered? We briefly discussed this topic in our previous video, The Pyramid That Knew Pi. Today we will delve deeper into the topic, discussing the speed of light and its relationship to the pyramid. When a mystery presses too closely against established knowledge, the first response of science is not wonder, but caution. This is not a flaw, it is a safeguard. Every discipline is built on hard-won standards of evidence, and anything that appears to leap across centuries, cultures, and technologies without a clear causal chain is met with resistance. The claim surrounding the Great Pyramid's latitude and the speed of light is no exception. Mainstream Egyptology steps back almost immediately. For decades, leading scholars such as Mark Lehner and Zahi Hawass have emphasized a clear position. The pyramids, they argue, were royal tombs, monumental, yes, symbolically rich, certainly, but rooted firmly in the social, religious, and political realities of Old Kingdom Egypt. Their construction, while astonishingly precise, is explained through human organization, skilled labor, and incremental technological refinement, not through lost sciences or encoded physics. From this perspective, the latitude correlation is not just unlikely, it is methodologically unsound. The first objection is foundational. The meter did not exist in ancient Egypt. It was defined during the French Revolution in the late 18th century as 1/10,000,000th of the distance from the equator to the North Pole along a meridian. This definition itself was revised multiple times, eventually becoming tied directly to the speed of light. To suggest that a structure built around 2600 BCE encodes a value expressed in meters per second appears, on its face, anachronistic. Physicists echo this objection from their own domain. The speed of light was not precisely measured until the 19th century, through experiments conducted by scientists such as Hippolyte Fizeau and Léon Foucault, and later refined by Albert Michelson. Its role as a fundamental constant emerged gradually, crystallizing with James Clerk Maxwell's equations in the mid-19th century and reaching full conceptual significance with Albert Einstein's theory of relativity in the early 20th century. Before this, light was not understood as a universal speed limit. It was a phenomenon, not a structural constant of reality. From this vantage point, the idea that ancient builders encoded the speed of light appears untenable. How could a civilization lacking modern instruments, modern units, and modern theoretical frameworks encode a value whose significance would only be understood thousands of years later? There is also the matter of decimal latitude. Decimal degrees are a modern convention. Ancient civilizations divided circles differently, often into 360 degrees, but even this system was not universally applied in architectural practice. Egyptian surveying relied on ropes, sightlines, and ratios, not angular subdivisions expressed numerically. Latitude as a decimal number is a product of modern cartography, refined through centuries of navigation, astronomy, and eventually satellite geodesy. From the orthodox perspective, the correlation exists only because modern observers choose to express Earth's surface in a particular numerical language. Change the language, and the meaning disappears. This is the heart of the refusal. To Egyptologists, the pyramid is not a message encoded for a future scientific civilization. It is a monument deeply embedded in its own time, culture, and belief system. To physicists, constants are meaningful only within coherent theoretical frameworks, not as isolated numbers waiting to be discovered in stone. And yet, even within this refusal, cracks begin to appear. Because the Great Pyramid already forces mainstream scholarship into uncomfortable territory. Its precision is not theoretical, it is measurable. The pyramid's base is level to within a few centimeters across an area larger than several football fields. Its sides are aligned to true north with an error of only a few arc minutes. Modern surveyors using advanced equipment have confirmed these facts repeatedly. Engineers acknowledge that achieving such precision today would require careful planning and sophisticated instrumentation. How was this done? Explanations exist. Stellar alignment methods, particularly observations of circumpolar stars, are widely accepted. Kate Spence, an Egyptologist at the University of Cambridge, proposed a method involving simultaneous alignment with Kochab and Mizar to explain the pyramid's orientation. Her model is respected, debated, and refined, but it acknowledges something essential. The builders possessed astronomical knowledge of remarkable sophistication. This alone does not imply encoded constants, but it establishes a precedent. The pyramid already exceeds what was once assumed possible for its time. The same tension appears in discussions of the pyramid's geometry. When earlier analyses revealed that the pyramid's perimeter-to-height ratio approximates pi, Egyptologists were quick to caution against retrofitting Greek mathematics onto Egyptian architecture, and they were right to do so. The Egyptians did not conceptualize pi as an abstract constant in the Greek sense. Yet mathematical historians also acknowledge that Egyptian methods, particularly their use of ratios and fractions, could yield highly accurate approximations of circular relationships without formal theory. The Rhind mathematical papyrus, dating to around 1650 BCE, demonstrates that Egyptian scribes were capable of sophisticated geometric reasoning. In other words, the absence of modern notation does not imply the absence of functional understanding. This is where the unit problem begins to soften. Physicists themselves admit that constants are not tied to units. The numerical value of the speed of light changes depending on the system used. In natural units, often favored in theoretical physics, the speed of light is simply 1. What matters is not the number, but the role the constant plays in relating quantities. As physicist John Barrow once noted, constants are not numbers in isolation, they are relationships. If ancient builders encoded relationships rather than values, then modern units would merely reveal those relationships in an unexpected form. This does not prove intention, but it reframes the objection. The refusal persists, but it is no longer absolute. Even skeptics acknowledge that the pyramid's location is unusual. It sits near the geographic center of Earth's landmass distribution. It occupies a latitude that, when expressed numerically, produces an unsettling coincidence, and it does so while belonging to a structure already known for encoding mathematical relationships in its proportions. Mainstream science, bound by discipline, cannot accept implication without mechanism. There is no known historical pathway by which 4th dynasty Egyptians could have conceptualized a universal speed limit. There is no textual evidence describing such knowledge. There are no inscriptions proclaiming cosmic constants. And yet the pyramid itself remains mute. It neither confirms nor denies. This is the refusal stage of the journey, the moment when rational caution pushes back against curiosity, when institutions protect coherence over speculation, when the safest answer is coincidence. But safety is not a resolution. Because the pyramid already stands as a contradiction to earlier assumptions, each generation revises what it believes ancient people could know. What once seemed impossible becomes merely unexplained. What once seemed fringe becomes quietly reclassified as advanced. And so a deeper question emerges, not as rebellion against science, but as loyalty to it. What if the problem is not that the Egyptians lacked modern units? What if the problem is that modern observers mistake units for meaning? If the language is wrong, the message will always appear accidental. And that is where the refusal begins to falter. Because the pyramid does not ask to be believed. It only asks to be accounted for. And the next question lies precisely there, in the growing suspicion that the unit problem itself may be the wrong question to ask. When a mystery refuses to resolve, the journey does not continue alone. It finds a guide. Not a prophet, not a believer, but an idea that quietly reframes the terrain itself. In this case, the guide does not arrive from the heavens or from lost manuscripts, but from the ground beneath our feet. What if the earth itself is the measuring stick? This question marks a turning point. Because if the Great Pyramid is not measured against modern units, but against the planet it stands upon, then many objections dissolve at once. Meters become incidental. Decimal notation becomes cosmetic. The focus shifts from numbers as symbols to numbers as relationships. This line of thought is known broadly as geodetic scaling theory. It is not a single doctrine, nor is it accepted as orthodox science. It is a collection of observations made over more than a century by surveyors, astronomers, engineers, and a handful of physicists who noticed something unsettling. Certain ancient monuments appear to reflect planetary dimensions with surprising consistency. The first figure to articulate this publicly was not a mystic, but a scientist. Charles Piazzi Smith was the Astronomer Royal for Scotland in the mid-19th century. Trained in rigorous observation and deeply familiar with precision measurement, Smith traveled to Giza in the 1860s with state-of-the-art surveying instruments of his time. His goal was not to validate myth, it was to measure. What he found disturbed him. Smith confirmed that the Great Pyramid's alignment to true north exceeded anything he had previously encountered in ancient architecture. But more troubling were the dimensions themselves. When Smith examined the pyramid's original height and perimeter, he noticed that when scaled by a factor of 43,200, the resulting values closely approximated Earth's polar radius and equatorial circumference. This number, 43,200, was not arbitrary. It is twice 21,600, the number of arc minutes in a circle. Each degree of latitude is divided into 60 arc minutes. Multiply 360 degrees by 60, and the full circle of Earth's rotation contains 21,600 arc minutes. Doubling that number produces 43,200, a scaling factor that links angular measurement to linear distance. In modern geodesy, this relationship is fundamental. It is how maps translate angles into kilometers. Smith did not invent this principle. He noticed that the pyramid appeared to embody it. When the pyramid's height is multiplied by 43,200, the result approaches the Earth's polar radius. When the pyramid's base perimeter is multiplied by the same factor, the result approaches the Earth's equatorial circumference. Not exactly, not perfectly, but well within tolerances that cannot be dismissed casually. Smith published these findings in his work, Our Inheritance in the Great Pyramid, which was met with fascination, skepticism, and eventual marginalization. Some of Smith's later conclusions drifted into speculative territory, and mainstream science rightly distanced itself from his broader claims. But the measurements themselves were never fully invalidated. That distinction matters. Later researchers returned to the same data with more restraint. In the 20th century, engineers and surveyors revisited pyramid measurements using improved techniques. Figures such as J.H. Cole, whose 1925 survey of the Great Pyramid remains one of the most respected, confirmed that earlier measurements were broadly accurate. The pyramid's original dimensions, while subject to erosion and casing loss, could be reconstructed with reasonable confidence. With better Earth models, including refined values for polar radius and equatorial circumference, researchers noticed something intriguing. The discrepancies between the pyramid-scaled values and Earth's dimensions were often smaller than expected, sometimes within fractions of a percent. Mainstream scholars cautioned against overinterpretation. Earth is not a perfect sphere. Its radius varies. Ancient builders could not have known precise modern geodetic values. All of this is true, but the pattern refused to disappear. By the late 20th and early 21st centuries, a new generation of independent researchers, many with backgrounds in engineering, surveying, or applied mathematics, revisited geodetic scaling with modern data. Some explored whether the pyramid's latitude, dimensions, and orientation collectively formed a coherent Earth-referenced system rather than isolated coincidences. One such avenue involved the relationship between the pyramid's placement and Earth's rotational geometry. The Great Pyramid sits remarkably close to the latitude that bisects Earth's landmass by area. While the exact calculation varies depending on continental definitions and sea levels, the observation remains provocative. The pyramid is not randomly placed within Egypt. It occupies a geospatially significant zone. This alone does not imply intent. But when combined with scaling relationships and astronomical alignment, it adds weight to the hypothesis that location mattered as much as form. Another element enters here: precession. Earth's axis slowly wobbles over a cycle of approximately 25,920 years, known as the precession of the equinoxes. This number is not obscure. It appears repeatedly in ancient cosmologies, mythologies, and numerical systems. Divide it by 60, and it yields 432. Multiply it by 100, and it yields 43,200. The appearance of this number across cultures has been noted by historians such as Giorgio de Santillana and Hertha von Deschend in their controversial but influential work, Hamlet's Mill. While their interpretations are debated, their central observation stands. Certain numbers tied to astronomical cycles recur with unusual persistence. In this light, 43,200 ceases to look accidental. It becomes a bridge between time, rotation, and space. Critics argue correctly that ancient Egyptians did not leave explicit records stating such intentions. There is no inscription declaring the pyramid a scale model of Earth. There is no surviving text outlining geodetic theory. But absence of explanation does not equate to absence of knowledge. Ancient engineering often encoded understanding through practice rather than prose. Medieval cathedral builders did not write treatises on stress distribution, yet their structures obey principles modern engineers now formalize mathematically. Knowledge can be operational without being theoretical. This is where the guide speaks most clearly. If the pyramid is scaled to Earth, then the Earth itself becomes the unit. The planet's rotation defines time. Its circumference defines distance. Its axis defines orientation. No meters are required, no seconds, only ratios between planetary features and architectural ones. Under this framework, the latitude correlation with the speed of light takes on a different character. Latitude is angular. Angular measures are ratios. If the pyramid's location encodes an angular value that later maps cleanly onto a physical constant, the coincidence is not between stone and meters. It is between geometry and physics. Modern physicists acknowledge that certain constants may be derivable from deeper geometric principles not yet fully understood. The shape of space-time, the topology of the universe, and the boundary conditions of cosmic inflation all influence fundamental values. The idea that geometry and physics are inseparable is not fringe. It is central to general relativity. Einstein himself described gravity not as a force, but as geometry. If reality is structured geometrically, then encoding meaning through geometry is not naive, it is profound. This does not require ancient Egyptians to know relativity. It requires only that they observed relationships between earth, sky, and number with extraordinary care, and chose to express those relationships in enduring form. Still, skepticism remains appropriate. Modern geodetic researchers who explore these ideas often emphasize probability rather than proof. They frame their findings as anomalies, not conclusions. Some, like Robert Bauval, have focused more on stellar correlations, such as the Orion alignment theory, which itself remains contested. Others have examined Earth scaling as part of broader sacred geometry traditions rather than explicit scientific knowledge. What unites them is not certainty, but discomfort. The Great Pyramid continues to behave as though it belongs to a framework larger than funerary architecture. It resists simplification. It accumulates meaning rather than shedding it. And this is the narrative turn. If Earth itself is the reference, then meters are irrelevant. Decimal degrees are merely a lens. The pyramid does not encode modern numbers. It encodes relationships that modern numbers happen to reveal. Under this view, the latitude speed of light correlation is not evidence of ancient physics textbooks carved in stone. It is evidence of something subtler, a way of thinking that treats Earth as a living coordinate system, a cosmic instrument embedded in a larger order. The guide does not promise answers. It only changes the direction of travel. Because once the Earth becomes the measuring stick, the pyramid stops being a structure and starts behaving like a diagram, and that raises a question that cannot be ignored any longer. If the Great Pyramid measures the Earth, then what else might it be measuring? The genius of the Great Pyramid is often misinterpreted through the lens of modern mathematics. Visitors, engineers, and scientists alike are tempted to describe its slopes in degrees, to calculate angles, or to invoke trigonometric formulas that did not exist for thousands of years after its construction. To do so is to impose a language on a people who spoke another entirely. The builders of Giza did not think in angles the way we do. They thought in ratios. They measured relationships, not abstractions. They built with what could be expressed on rope, reed, and cubit. The Egyptians had a system for expressing slope known as the seked. This is, in essence, a measure of the horizontal displacement corresponding to a vertical rise of 1 cubit. Modern engineers might think of it as a tangent expressed in practical terms rather than mathematical notation. The seked allowed architects and surveyors to translate abstract proportions into actionable measurements, to communicate design across teams of masons, and to maintain astonishing precision without recourse to trigonometry. It was a language of ratios, of relational geometry, of functional mathematics encoded into everyday tools. Sekeds were written in the form of fractional units. The Rhind mathematical papyrus, one of the most important surviving documents of Egyptian arithmetic and geometry, contains examples of calculations that reconstruct pyramid slopes, volumes, and angles using seked. For instance, the slope of a pyramid could be expressed as a ratio of 7 palms for every 5 cubits of rise, a relationship immediately understandable to a master builder. This system did not require calculating sine, cosine, or tangent. Yet, functionally, it achieved the same result: a precise slope, reproducible across hundreds of meters, even thousands of stones. Mathematical reconstruction of the Great Pyramid slopes confirms this. Scholars such as John Legon and Miroslav Werner have examined the base and height, comparing them to documented seked ratios. Their research shows that the original pyramid slope corresponds closely to a seked of 5.5 palms per cubit, equivalent to a modern angle of approximately 51 degrees and 51 minutes. This was not approximate. Measurements across the pyramid's 4 sides show astonishing uniformity, deviations measured in mere millimeters over hundreds of meters. The Egyptians achieved this without protractors, without trig tables, without calculators, but with ratios, a language of practical geometry. The key insight here is that ratios are dimensionless. Unlike modern measurements that rely on units of meters, feet, or degrees, a ratio is universal. It exists independently of any measuring stick. 7 palms per 5 cubits represents a proportion, not a distance. It survives translation between cultures, technologies, and millennia. It is in this sense that the pyramid becomes more than architecture. It becomes a repository of abstract relationships, relationships that can later be expressed in units we understand today, and in some cases in ways we might not have anticipated. It is this principle that allows modern researchers to notice correspondences that would have been invisible to the builders themselves. When we observe that the latitude of the pyramid, expressed in decimal degrees, aligns with the speed of light in meters per second, we are translating a practical ratio-based system into the language of modern physics. The builders may never have known what light was, much less that it had a constant velocity measured in meters per second. Yet their ratios, embedded in stone, can now be read through our instruments as if they encode a law of the universe. This does not imply intentionality in the modern sense, but it does suggest that ancient mathematics was capable of expressing relationships far more subtle than previously acknowledged. Seked ratios encoded slope, scale, and alignment with remarkable fidelity. They were not limited to architectural applications. Ratios can express motion, distance, time, and celestial relationships. In this framework, the pyramid is a kind of functional equation written in stone rather than symbols, bridging earth, sky, and human perception. Egyptologists emphasize the importance of understanding these systems on their own terms. Paul T. Nicholson, an authority on ancient Egyptian mathematics, has noted that the Seked represents a practical solution to a geometric problem: how to achieve a stable slope for monumental construction. The genius lies in the reproducibility, the precision, and the universality of the relationships. It is mathematics as action, not abstraction. And when the pyramid is scaled to the Earth, when the planet itself becomes the measuring stick, these ratios begin to resonate in ways the original builders could not have anticipated. Mathematical reconstructions also illuminate the interplay between the Seked system and other elements of pyramid design. Horizontal displacement, vertical rise, and the alignment of corners all interact. Modern 3D reconstructions, informed by archaeological measurements and laser scanning, reveal that the slope ratio interacts with orientation, base geometry, and even astronomical alignment. The Seked was not an isolated calculation. It was part of an integrated system of measurement, a functional code that guaranteed both structural stability and cosmological alignment. What makes this system even more remarkable is that it can be expressed in multiple units without loss of integrity. One can convert palms to cubits, cubits to meters, meters to feet, and the underlying relationship remains the same. This is the principle that allows dimensionless ratios to survive unit transformations across millennia. It is why modern observers can express relationships in meters per second, degrees, or decimal fractions, and still find correspondences with ancient structures. The language changes, but the pattern endures. Herein lies the subtle power of the Seked. It encodes constants invisibly, not in symbolic form, but as functional relationships between physical quantities. Height, base, orientation, and distance all interact through ratios that govern the shape and stability of the pyramid. These ratios are robust, they are reproducible. They are independent of the measuring system applied. And in the modern mind, accustomed to abstract constants and physical laws, they appear almost prophetic. It is not necessary to claim that the Egyptians encoded modern physics, yet the system they used allows for modern interpretations that reveal unexpected correspondences. Ratios that ensured the structural stability of a 4,500-year-old monument can now be read through the lens of modern science as relationships that echo constants like pi, phi, and even, astonishingly, CE, the speed of light. The parallels are functional, not literal, but their existence demands attention. They suggest that when geometry is treated as a living language, it can express truths far beyond the immediate practical concerns of construction. Researchers such as John Legan and Peter Hodgson have emphasized that these correspondences, while intriguing, should be approached cautiously. The pyramids were built for the gods, for kings, and for cosmological alignment. Any suggestion of encoding modern constants is speculative. Yet the ratios are there. They exist independently of measurement systems. They are silent, precise, and persistent. They invite investigation without demanding belief. And here the question is, if ratios can encode structural stability, planetary alignment, and cosmological relationships invisibly within stone, then one cannot help but wonder, could a ratio exist that, when interpreted through modern units, reveals a constant that humanity would only name millennia later as c, the speed of light? Could it be that the language of the builders, grounded in Seked, allowed them to express the principles of reality itself, not in the abstract, but in practical, enduring form? The call is subtle, almost imperceptible, yet irresistible. Numbers refuse to be silent. Ratios persist across time. And the Great Pyramid, constructed through a language of functional mathematics, waits quietly for those who can read it. Long before satellites, chronometers, or GPS, the sky was the map. The stars were not decoration. They were instruments, precise and consistent, capable of revealing position, direction, and time with astonishing accuracy. To understand how the Great Pyramid's latitude might have been known, one must first look upward to the heavens that guided human observation for millennia. The Egyptians were keen observers of the night sky. They tracked the rising and setting of stars, particularly those that never dipped below the horizon, the circumpolar stars. These stars rotate around the celestial pole, never disappearing from view. Their circular paths offer a natural clock, a reference system that marks the passage of time, the season, and crucially, position. By observing their height above the horizon, one could determine latitude with precision. Modern reconstructions of ancient Egyptian astronomy support this possibility. Researchers such as Kate Spence at Cambridge have shown that the precise orientation of the Great Pyramid toward true north could have been achieved by observing pairs of circumpolar stars, such as Kochab and Mizar, and aligning structures when they were vertically aligned. Spence's model explains deviations in orientation over time and suggests the builders possessed both observational skill and a conceptual understanding of stellar motion. Such methods do not require modern instruments, only careful observation, patience, and an understanding of patterns in the sky. Stellar transit observation, noting when a star crosses a fixed line of sight, could also have been employed to determine latitude. This is a technique used by navigators for centuries, long before the formal development of trigonometry. By measuring the angle of circumpolar stars at culmination, ancient surveyors could fix a site's position relative to the celestial pole. Though precise instrumentation was rudimentary, repeated observation and communal verification allowed astonishing accuracy, as seen in the pyramid's near-perfect alignment and its latitude, 29.9792458 degrees north. Precession, the slow wobble of Earth's axis over a 25,920-year cycle, was not fully understood by the Egyptians, yet long-term observations could reveal its effects in subtle ways. By tracking star positions across generations, they would notice slow shifts, giving rise to calendars, heliacal rising calculations, and timing for festivals. Scholars like Robert Bauval have emphasized that while the Egyptians could not calculate precession numerically as we do, they observed its consequences through practical astronomy, encoding this awareness in architecture, alignment, and ritual. Modern surveying confirms what the ancients achieved. Laser scans, total station measurements, and satellite geodesy reveal that the Great Pyramid is aligned to true north within a few arc minutes. The original surveyors did not guess. They measured, and their measurements correspond closely to a latitude that, when expressed in modern decimal degrees, is 29.9792458. This is not rounding, this is exactitude preserved across 4.5 millennia. Astronomical alignment models provide further support. By reconstructing the night sky at 2600 BCE, researchers can simulate which stars were visible and which pairs could have served as references for alignment. These models suggest that the latitude itself while perhaps not expressed numerically by the Egyptians, was functionally encoded in the choice of location and in the orientation of the pyramid. Observing circumpolar stars, they could identify a line of latitude with remarkable precision, enough to place a structure consistently in relation to both the sky and the horizon. This precision undermines the notion that the pyramid's placement was arbitrary. Latitude is not guesswork. It is measurable, repeatable, and verifiable. The combination of circumpolar observation, stellar transit alignment, and careful terrestrial measurement provides a toolkit that could allow the ancient Egyptians to situate the pyramid exactly where they intended. The fact that this latitude coincides with a number expressing a modern physical constant adds tension, but the astronomical basis alone is sufficient to explain how the builders knew their position on Earth with remarkable accuracy. Yet awareness of position is only half the story. Accuracy of observation and the technical skill to realize it in stone are extraordinary. Surveying methods likely involved sighting poles, plumb lines, and ropes, calibrated in cubits. Teams of skilled workers would have verified measurements repeatedly. Misalignment even by a few degrees over hundreds of meters would produce structural asymmetry or deviation from intended orientation. The surviving pyramid demonstrates that these measurements were not approximate. They were engineered with precision consistent with repeated astronomical observation. Here, the narrative turns toward the question of intention. The builders had the ability to determine latitude. They could measure the Earth's rotation indirectly through the stars, replicate ratios through sect, and maintain geometrical fidelity across massive constructions. This was not happenstance. It was expertise grounded in the observation of the cosmos. And so the stage is set for a profound question. If the builders knew exactly where they were on Earth, if the stars and ratios allowed them to anchor a monument in precise relation to the planet itself, then why choose this particular location? What made this latitude, this point on the surface of the Earth, sacred, functional, or significant enough to host a structure whose scale and precision continue to baffle modern engineers and scientists alike? The answer does not emerge here. It waits, unspoken, teasing curiosity. Because knowing your place on Earth is one achievement, but choosing a location that aligns with a constant later defined by physics is another. And the Great Pyramid, silently observing the sky for millennia, invites the next step of discovery. The number 299,792,458 is more than a figure. It is the threshold at which the universe itself permits cause and effect to travel. Known as the speed of light, commonly designated as c, it defines the ultimate limit in our cosmos. Nothing can move faster. No information can propagate beyond it. It is the measure by which space and time themselves are stitched together, the framework underlying all motion, all energy, all observation. Albert Einstein revealed the profound significance of this number in the early 20th century. In his theory of special relativity, he showed that the speed of light is not simply the velocity of photons, it is the boundary condition of reality. Space and time are not independent arenas, but elements of a single four-dimensional fabric called space-time. Light, moving at c, is the constant that connects them. Every motion, every interaction, every force in the universe is constrained by this limit. The importance of c extends beyond theory. In the mid-20th century, the definition of the meter itself was reimagined in terms of the speed of light. Prior to this, the meter had been based on physical artifacts, such as a platinum iridium bar kept in Paris, or geodetic measurements of the Earth made in the 18th and 19th centuries by surveyors including Jean-Baptiste Joseph Delambre and Pierre Méchain. In 1983, the General Conference on Weights and Measures redefined the meter. It is the distance light travels in a vacuum in exactly 1 divided by 299,792,458 of a second. By anchoring units to a fundamental constant rather than an arbitrary object, science recognized that c is not merely a measurement of speed, it is the backbone of the metric system itself. The recognition that light defines the scale of reality transforms its role from mere illumination to structural principle. Light is not simply what allows us to see, it is what constrains what can be seen, what can happen, and what can exist. It determines the possible paths of planets, the spread of galaxies, and the flow of time itself. Through light, the universe becomes intelligible, measurable, and predictable. To physicists, C is the keystone of all interactions. Electromagnetic waves, gravitational influence in relativity, energy-matter equivalence, all depend on the constancy of light's velocity. Maxwell's equations, formulated in the mid-19th century, revealed that light is an electromagnetic phenomenon, inherently linked to electric and magnetic fields. Einstein's later work expanded this insight, showing that nothing with mass can reach the speed of light, and that motion alters both time and length relative to the observer. In other words, c is not a property of light alone, it is a property of space-time itself. Modern measurements of c have reached astounding precision thanks to the work of numerous scientists across decades. Hippolyte Fizeau and Léon Foucault made the first reasonably accurate measurements in the 19th century using rotating mirrors and light beams to gauge velocity. Albert Michelson refined these measurements with increasing precision, culminating in values that paved the way for the modern definition. Each experiment demonstrates the constancy of c across space, orientation, and time, underscoring its role as a fundamental law of the universe. In 1983, the meter's redefinition made this principle practical. By fixing the speed of light at exactly 299,792,458 meters per second, the unit of length became derived from the behavior of the universe rather than a terrestrial artifact. Science had turned the cosmic constant into a measuring stick, ensuring that every meter, every kilometer, every scientific calculation reflects the structure of reality itself. The speed of light was no longer only a phenomenon to be observed, it became the standard by which all distances are quantified. Philosophically, this number challenges our perception of reality. Light is not merely a tool for seeing, it is the framework of being, the measure of possibility, the silent arbiter of existence. Without c, space-time loses its coherence, motion loses meaning. The universe collapses from a predictable structure into unbounded chaos. It is in this context that the coincidence becomes more than curiosity. The pyramid, a monument of stone placed on the surface of the Earth 4,500 years ago, sits at a latitude that, expressed in decimal degrees, mirrors the speed of light in meters per second. Modern units are irrelevant to the builders. They knew nothing of Einstein, Maxwell, or Michelson, yet in some way the numbers align. Geometry, astronomy, and geodesy converge in a form that mirrors a fundamental constant, a number that defines the cosmos and structures the universe. This raises profound questions. If light governs the limits of the universe, if it binds space and time into a coherent whole, what does it mean for a civilization to encode a number so central to reality into the location of a monument? Could ratios alone, approximate a value that would only centuries later be recognized as the ultimate speed limit? Could the pyramid, in its silent solidity, be a statement not of kingship or ritual, but of observation, understanding, and perhaps something approaching cosmic awareness? The implications ripple outward. Light is not decoration, not utility, not secondary. It is the measure of existence. And yet here it appears reflected in stone, in sand, in human endeavor long before science named its constancy. A question emerges. What kind of civilization could conceive, intentionally or otherwise, of a value that defines the structure of reality itself? Human beings are pattern-seeking creatures. From the earliest constellations traced across the night sky to modern data analysis, the mind is wired to connect dots, to find structure, to impose meaning. This instinct has ensured survival, but it also creates a problem. We see relationships where none may exist. In science, this tendency has a name. It is called apophenia, the perception of meaningful patterns in random data. Any serious inquiry into the latitude and speed of light correlation must begin here, not with wonder, but with restraint. The coincidence theory argues that with enough numbers, overlaps are inevitable. The Earth is vast, monuments are many, constants of physics are numerous. Given sufficient combinations, some will resemble one another. Skeptics point out that latitude is expressed in decimal degrees only because modern cartography demands it. Change the coordinate system, change the unit base, or use radians instead of degrees, and the numerical similarity disappears. Under this view, the match between 29.9792458 degrees north and 299,792,458 meters per second is a projection of modern measurement onto an ancient world that did not share those conventions. Statistically, this argument has weight. In large datasets, improbable alignments occur routinely. Probability theory tells us that rare events are not only possible but expected given enough trials. Physicist David Hand has famously described the improbability principle, noting that extraordinary coincidences happen more often than intuition suggests. Applied here, the Earth's surface offers an enormous canvas. Any latitude from 0 to 90 degrees north or south contains millions of possible decimal expansions. Somewhere a monument was bound to sit on a number resembling a known constant. Yet this explanation, while mathematically defensible, does not end the inquiry. It merely establishes a baseline. The real question is not whether coincidences can occur, but whether this particular coincidence behaves like a random one. And when examined closely, it begins to resist that classification. First, consider precision. The latitude of the Great Pyramid is not approximately 29.98 degrees north. It is 29.9792458 degrees north, matching the speed of light to 7 significant digits when the decimal is shifted. This is not a rough echo, it is a near-exact correspondence. In statistical terms, increasing precision dramatically lowers probability. A match to 2 or 3 digits would be trivial. A match to 7 is not. The probability space collapses rapidly as precision increases. Second, consider context. This is not an isolated monument placed haphazardly. The Great Pyramid is already mathematically saturated. Its perimeter, divided by twice its height, closely approximates pi. Its slopes encode rational ratios expressible through seced. Its orientation to true north surpasses that of most modern buildings. Its proportions reflect scaling relationships that reappear in Earth measurements, particularly when examined through the 43,200 ratio. To treat the latitude correlation as independent of this context is statistically unsound. In probability theory, events are not evaluated in isolation when dependencies exist. Third, consider selection bias. Critics argue that the pyramid is singled out only because the match exists, but the pyramid has long been singled out for independent reasons, long before the speed of light correlation was noticed. Engineers, archaeologists, mathematicians, and physicists have studied it for centuries because of its anomalous precision and scale. This reduces the risk of cherry-picking. The object of interest was already under scrutiny for reasons unrelated to this particular number. Pattern-seeking bias becomes problematic when arbitrary data points are connected without constraint. Here, the constraints are unusually tight. The monument is singular. The number is singular. The match is precise. And the surrounding mathematical context is dense. In statistical terms, this increases signal relative to noise. To quantify the improbability, some researchers have attempted back-of-the-envelope calculations. While not definitive, they offer perspective. If one assumes a latitude range of 0 to 90 degrees and considers decimal expansions to 7 digits, the chance of randomly matching a specific 7-digit sequence is roughly 1 in 10 million. This does not account for negative latitudes, nor does it incorporate context or dependencies. It simply illustrates scale. When combined with the pyramid's known mathematical properties, the odds narrow further. At this point, skepticism often shifts to semantics. The builders did not use meters, they did not know seconds, they did not express angles in decimal degrees. All of this is true, but it may be irrelevant. The match does not require shared units, it requires ratios. The speed of light is a dimensioned quantity in modern terms, but when expressed as a ratio between distance and time, and when distance and time themselves are defined through Earth-based and astronomical cycles, the units become scaffolding rather than substance. This is where coincidence theory begins to strain. A purely random match would not align so cleanly with a monument that already encodes ratios connected to Earth, sky, and geometry. Nor would it emerge from a structure whose design language relies almost entirely on proportion rather than absolute measurement. The Egyptians did not need meters to encode relationships. They needed consistency. Scientific humility demands restraint. Coincidence remains possible. No responsible analysis claims certainty. Science does not advance by declaring meaning where evidence is ambiguous. But humility also demands openness. Meaninglessness is not guaranteed simply because an explanation is uncomfortable. Throughout scientific history, patterns once dismissed as coincidence later became foundational. Planetary orbits, spectral lines, even the cosmic microwave background were once curiosities before becoming pillars of understanding. The deeper issue is philosophical as much as statistical. Coincidence theory assumes that meaning must be intentional to be real. But nature itself is not intentional in a human sense, yet its patterns are meaningful. Mathematical constants emerge from reality without design. Ratios appear because they reflect structure. If ancient builders were careful observers of nature, they may have encoded relationships without knowing their future names. In this light, coincidence and intention are not opposites. They may be different expressions of the same underlying order. A pattern can be discovered rather than invented. A ratio can be preserved without being fully understood. The builders did not need to know the speed of light as modern physics defines it. They needed only to work within a system that reflected cosmic regularities. This reframes the debate. Instead of asking whether the pyramid intentionally encodes the speed of light, a question loaded with anachronism, a subtler question emerges. Is the pyramid aligned with a set of ratios and measurements that reflect deep properties of the Earth and cosmos, properties that modern science later formalized into constants? If so, the latitude correlation may not be a message, but a resonance. When coincidence is placed on trial, it does not collapse under scrutiny. But neither does it fully explain what is observed. The match is too precise, the context too rich, the monument too mathematically dense to dismiss casually. Something else may be at work, something that sits between randomness and design. Perhaps coincidence itself is the wrong lens. Perhaps the more appropriate question is not whether the numbers were meant to align, but whether both emerge from the same underlying order. And if that is the case, then the Great Pyramid is not defying probability. It is revealing structure. Across millennia and continents, humans have repeatedly returned to certain numbers as if drawn to them by intuition, necessity, or a hidden logic embedded in the cosmos itself. Pi, the ratio of a circle's circumference to its diameter, is perhaps the most enduring of these constants. Its first approximations date back to at least 1900 BCE in Egypt, recorded on the Rand mathematical papyrus, where scribes estimated pi as 256/81, yielding a value remarkably close to 3.16. In Babylon, around the same period, clay tablets suggest approximations of 3.125. Across cultures, the knowledge of circles, angles, and ratios appears independently. suggesting a human recognition of fundamental patterns rather than a shared tradition in the modern sense. Pi is not just a number. It is a bridge between linear measurement and curvature, between geometry and reality. Its mathematical significance extends beyond circles into spheres, oscillations, waves, and the very foundations of calculus, which would only emerge thousands of years later. Modern physics, through constants such as Planck's relation and the behavior of waves, repeatedly encounters pi in equations governing everything from planetary orbits to quantum probability distributions. To ancient builders, the practical implications of pi were equally profound, even if expressed without formal symbols. To approximate a circular base, to harmonize structural proportions, or to lay out celestial alignments, some understanding of the ratio of circumference to diameter was essential. In the Great Pyramid, the evidence of pi appears in the relationship between perimeter and height. The perimeter divided by twice the height yields a value that closely approximates pi. Researchers such as John Lagan have noted that while it is impossible to prove intentionality beyond doubt, the precision is extraordinary for the period. The choice to scale a monumental structure using proportional relationships that echo a universal constant demonstrates that Egyptian mathematics was both practical and abstract, operational and visionary. It allowed the builders to encode relationships that would remain stable and legible for millennia, independent of units, yet fully reproducible in modern metrics. This sophistication was not unique to Egypt. Across the ancient world, independent civilizations embedded constants in their monuments. In Greece, the Parthenon's proportions reflect phi, the golden ratio, approximating 1.618. Phi governs ratios found in spirals, plant growth, and aesthetic balance. Its appearance in architecture may have emerged from observation rather than calculation. In Mesoamerica, the Mayan temples exhibit repeated attention to harmonic ratios and lunar cycles. Their pyramids often align to solstices and eclipses, marking time with astonishing precision. These cultures, separated by thousands of kilometers and millennia, repeatedly engaged with similar mathematical patterns, suggesting a cognitive convergence rather than diffusion. Humans, it seems, are attuned to certain universal relationships, whether through observation of celestial patterns or the necessities of construction. Beyond geometry, some ancient architects explored cyclicity in time through spatial design. Temple spacing in Mesoamerican sites, for example, often aligns with lunar cycles, suggesting an understanding of astronomical periodicity. Modern archaeologists, using high-resolution mapping and software reconstruction, have noted that the interval between certain pyramid complexes approximates multiples of the lunar month, around 29.53 days. While caution is necessary, natural geography and ritual imperatives complicate interpretation, the alignment is statistically notable. It reflects an awareness of temporal patterns expressed in material culture, a recognition that spatial and temporal order can be encoded together. Acoustic resonance, too, has been carefully studied in ancient chambers, though scientific restraint is essential in interpretation. Researchers such as John Elliott and Joseph Schultz have used digital models and in situ measurements to investigate the frequency response of chambered spaces, including the King's Chamber of the Great Pyramid. Certain standing wave patterns occur at frequencies corresponding to musical intervals or human vocal resonance, yet no evidence proves intentionality. Nevertheless, the presence of harmonic properties indicates that builders understood the behavior of sound in enclosed stone volumes, whether for ritual amplification, ceremonial effect, or incidental consequence. Across cultures, stone structures, from dolmens in Europe to rock-cut temples in India, exhibit similar resonance characteristics, suggesting an intuitive or observational grasp of physical properties that precedes formal acoustical theory. The recurrence of pi, phi, lunar cycles, and harmonic proportions across cultures raises a provocative idea. These numbers are not mere artifacts of one civilization. They are emergent features of human interaction with geometry, astronomy, and the natural world. Independent discovery suggests universality. If one surveys ancient monuments from Egypt, Greece, India, China, and the Americas, similar numerical relationships appear repeatedly, even when the civilizations involved had no known contact. Patterns emerge in circles, ratios, orientations, and spatial temporal sequencing. The convergence of such constants across cultures points to a shared recognition of the underlying order of nature, expressed in stone, wood, and celestial alignment. Scientific studies reinforce these observations. Archaeological surveys provide precise measurements of pyramids, temples, and observatories. Laser scanning technology has confirmed that the base angles, side ratios, and axial orientations of certain monuments reflect values remarkably close to pi and phi. Astronomical reconstructions validate alignments with solar solstices, equinoxes, and lunar cycles. Acoustic models quantify resonant frequencies in ceremonial chambers. Each domain, geometry, astronomy, acoustics, offers independent verification, though always with a cautious acknowledgement of possible alternative explanations, from functional design to coincidental alignment. No single study proves intent to encode universal constants, yet collectively, the data indicate that ancient builders repeatedly engaged with measurable relationships whose significance endures today. Cultural context enriches this interpretation. Numbers carried symbolic, ritual, and religious weight. The Egyptians, for example, associated the circle with eternity, the cycle of the sun, and the divine principle of Ma'at. Ratios and proportions were not abstract but imbued with meaning. Construction, mathematics, and cosmology intertwined. In Mesoamerica, alignments with the sun, moon, and Venus were fundamental to ritual calendars. In India, temple geometry expressed cosmic order through yantras and mandalas. In Greece, mathematical harmony became the foundation of philosophy, art, and architecture. In each case, the constants, pi, phi, temporal cycles, were both practical tools and carriers of cultural significance. This confluence of mathematics, observation, and cultural meaning invites reflection. Modern science reads these monuments and identifies numerical coincidences, physical principles, and universal constants. Archaeologists recognize human ingenuity and adaptation. Historians note the interplay between practical necessity and symbolic expression. Together, these perspectives reveal that ancient humans, regardless of geography or era, were attuned to a set of relationships intrinsic to the physical and temporal worlds. The implications extend to the Giza Plateau. When the latitude of the Great Pyramid aligns numerically with the speed of light, it is set within a monument already rich with ratios, angles, and proportions connected to pi. The perimeter, the height, and the slope together encode relationships between circular and linear measurement. These constants, emergent through geometry and scale, suggest that the builders were working within a system capable of expressing relationships that transcend units and cultures. Pi appears in the structure not merely as a convenience, but as a functional ratio, ensuring proportional integrity, stability, and potentially cosmological correspondence. Across the globe, independent cultures approached similar problems and arrived at similar solutions. Pi-guided circular constructions, astronomical observations informed temporal design, harmonic principles shaped enclosed spaces, and ratios ensured structural stability. The repetition of these constants hints at a cognitive universality, a shared human sensitivity to certain fundamental truths. It is as though human beings, acting independently, were rediscovering an underlying order, encoded in material, accessible through observation, and persistent through time. The key insight is that the constants appear in functional contexts. They are not abstract exercises but operational tools, integrated with geometry, astronomy, acoustics, and ritual practice. They persist in a form that allows modern observers to recognize them, to measure them, and to test their precision. Scientific rigor confirms that these numbers are neither random nor trivial. They are consistent, replicable, and tied to measurable aspects of the physical world. The global recurrence of pi, phi, and other ratios, combined with precise spatial and temporal alignments, presents a provocative question. If independent civilizations, separated by thousands of kilometers and generations, discovered similar patterns, does it suggest a shared foundation of understanding, a human intuition attuned to the order of nature, or perhaps a fragment of knowledge transmitted across time and space that has since been forgotten? Are we witnessing the echoes of principles humanity once recognized universally, embedded in stone, and waiting to be reinterpreted through modern science? In this light, the Great Pyramid is not an isolated curiosity. It is part of a global phenomenon in which constants manifest repeatedly in architecture, astronomy, and acoustics. Its mathematical density, combined with precise astronomical alignment and geodetic scaling, situates it within a broader pattern of human engagement with numbers that govern form, motion, and rhythm. From the circle to the spiral, from lunar months to harmonic resonance, civilizations across the world seem to converge on the same truths, independently articulating constants that endure in both nature and culture. And so the question lingers: are these patterns coincidental, culturally driven, or evidence of something deeper? Is humanity merely rediscovering truths that were once universally understood, encoded across the globe in temples, pyramids, and observatories? Or do these constants emerge inevitably from the act of observation itself, independent of human intention, waiting to be recognized by any civilization attentive enough to look, measure, and record? The answer is not clear. Yet the recurrence of pi and other constants across cultures suggests that our ancestors, whatever their context, were attuned to a logic that transcends geography, time, and even mortality. The universe presents itself as a web of order and structure, yet the origin of that order remains shrouded in mystery. Physics provides equations, measurements, and predictions, but it does not answer why the cosmos is precisely as it is. Among the most profound puzzles are the constants, numbers that define reality with exquisite precision. The speed of light, Planck's constant, the gravitational constant, the fine structure constant, these are not arbitrary. Small variations in any of them would render stars unstable, chemistry impossible, and life unthinkable. This is the essence of what scientists call the fine-tuning problem. The parameters that govern the cosmos are not merely convenient. They appear balanced delicately, as though the universe itself were calibrated to permit complexity and consciousness. The anthropic principle attempts to give context to this observation. At its simplest, it states that the universe must be compatible with the existence of observers, for otherwise we would not be here to notice it. Some interpretations suggest that we see the universe as fine-tuned simply because if it were otherwise we could not exist. Others propose multiverses, with innumerable universes each sporting different constants, and we inhabit the rare pocket where life is possible. Yet even the most generous multiverse models fail to explain the apparent elegance with which these constants interlock. Why should numbers governing electromagnetism, gravity, and quantum mechanics converge in a configuration that allows stars to burn for billions of years, planets to sustain liquid water, and consciousness to emerge? Philosophers and physicists alike recognize a profound gap between description and explanation. Physics can measure the speed of light, calculate orbital resonance, predict electron behavior, and map the expansion of space. Yet it cannot account for why these numbers have the values they do. Max Tegmark, a contemporary theoretical physicist, has suggested that perhaps the universe is mathematical at its core, that reality itself is a structure of relations expressed through numbers. But even this elegant hypothesis does not tell us why this mathematical structure is instantiated in this particular universe rather than another. Science excels at describing patterns, but it often falls silent when asked about origin, purpose, or meaning. It is here that philosophy enters the conversation. The constants, so precise, so enduring, evoke questions that reach beyond laboratories and telescopes. Could it be that they are not arbitrary at all? Could they be preserved knowledge, encoded in forms accessible to human observation? If a civilization capable of measuring and aligning structures with astonishing precision encoded ratios and proportions that reflect these constants, then perhaps the universe is not simply fine-tuned in isolation. Perhaps it has been mirrored, remembered, or at least reflected in human endeavor. Consider the Great Pyramid, whose latitude numerically echoes the speed of light when expressed in modern decimal degrees. The builders did not possess meters, seconds, or an understanding of electromagnetic theory. They operated with ratios, cubits, and celestial observation. Yet the precision of their work allows a modern observer to draw connections that were inconceivable to the ancients. The relationship between physical constants and architectural ratios is not proof of intent, but it challenges assumptions about the boundary between discovery and coincidence. Are constants imposed by nature, or can they also emerge through repeated observation and practical expression, preserved in human structures across time? The philosophical weight of this crossing is substantial. When science reaches its limits, the mystery is not weakness, it is insight. A physicist can describe the speed of light, calculate its effects on time dilation, and predict its consequences for high-velocity travel. Yet no experiment, no equation can explain why c takes the value it does, or why light behaves consistently across the universe. Similarly, mathematics can describe pi, phi, or ratios embedded in ancient monuments, but it cannot account for why human minds independently rediscover these relationships across continents. In both cases, the observer confronts a gap between knowledge and recognition, between calculation and comprehension. This crossing between physics and philosophy highlights another tension. The universe is simultaneously knowable and enigmatic. Constants provide predictability. Ratios, measurements, and physical laws give structure to reality. Yet their origin, their significance beyond functional use, remains speculative. To stand before a pyramid aligned to true north and scaled with ratios that encode mathematical relationships is to confront the universe's order in a tangible form. One is reminded that human curiosity, like the cosmos itself, is persistent, probing, and capable of detecting subtle harmonies that exceed immediate explanation. Some modern scientists have cautiously approached these questions. Martin Rees, former Astronomer Royal, has remarked on the coincidences in physics with careful precision. He points out that while constants could, in principle, take many values, we inhabit a universe where the balance allows complexity. He stresses that this does not imply intention, but invites reflection. Similarly, Freeman Dyson has speculated on the longevity of physical laws and the possibility that observers imprint their own recognition onto the universe, suggesting a feedback loop between cognition and structure. Such reflections bridge the empirical with the philosophical without abandoning rigor. It is in this space that the idea of remembered constants emerges. If fundamental numbers define the constraints of reality, and if intelligent beings encode proportional knowledge into monuments, instruments, and measurement systems, then knowledge of constants may exist in forms beyond direct calculation. The Great Pyramid, the lunar-aligned temples, and the repeated discovery of pi and phi across cultures may represent echoes of such knowledge. They are records of human engagement with universal relationships, preserved as ratios, as alignments, as functional constructions. Yet caution is essential. The crossing between physics and philosophy must not overreach. One cannot claim that the pyramid intentionally encodes C in the sense modern physics defines it. One can, however, recognize that ratios, geometry, and alignment produce correspondences that invite reflection. The human mind detects patterns. The universe exhibits regularity. When these intersect in a monument, the result is a convergence of natural law, human ingenuity, and philosophical speculation. This perspective reframes our understanding of constants. They are not merely numbers in a textbook. They are measures of possibility, constraints on causality, and windows into the structure of reality. They are also mirrors, reflecting the sophistication of human observation, the universality of mathematical insight, and the persistent curiosity that drives civilizations to build, measure, and explore. They link the cosmos to cognition, the abstract to the tangible, the eternal to the temporal. When the Great Pyramid and the speed of light are considered together, the mind encounters a subtle yet profound suggestion. Perhaps constants are not entirely hidden. Perhaps they can be expressed, approximated, or even remembered through careful observation, through the translation of ratios into stone, through the alignment of human activity with celestial patterns. Science can measure and describe, but it cannot yet fully explain the deeper resonance. Philosophy steps in to ask whether our measurements are discoveries, or if they are rediscoveries of relationships that civilizations before us already intuited and encoded in ways we are only beginning to perceive. And so the question arises, what if the constants that define reality are not random, not arbitrary, but remembered, preserved, and expressed across generations through observation, construction, and mathematical intuition? If the universe permits observation, and observation permits recognition, then perhaps the line between discovery and memory is thinner than we realize. In the intersection of physics and philosophy, the Great Pyramid stands as a testament, inviting us to consider that numbers, ratios, and constants are not only descriptive but also witnesses, subtle markers of knowledge that persist, waiting for the attentive mind to see them once more. Long before printing presses or digital archives, human knowledge traveled in fragile forms. Words spoken, shapes drawn, and stones set were the vessels of memory. Across continents and millennia, civilizations found ways to preserve insights that could not be held in fleeting human memory alone. In Egypt, the meticulous orientation of temples, the proportional systems of pyramids, and the codified use of cubits served as more than functional tools. They were mnemonic devices. Geometry became language, a way to record not only measurements, but understanding. The principle of sacred geometry illustrates this vividly. Circles, triangles, and squares were not merely aesthetic choices, but deliberate encodings of cosmic and terrestrial order. They allowed knowledge to endure beyond the lifespan of any individual. A ratio embedded in a temple's layout could communicate astronomical periods, cycles of the moon, or the relationship of the structure to the cardinal directions. In this sense, geometry acted as both instruction and memory. It ensured that builders, priests, and surveyors could reproduce complex concepts across generations without the need for written explanation. Knowledge transmission often depended on dual channels, oral and architectural. In Mesopotamia, the ziggurats were aligned and proportioned according to celestial observations. Knowledge likely passed through apprenticeship and ritual recitation. In the Indus Valley, precise urban grids suggest standardized units and surveying practices, yet no deciphered script tells us exactly how these practices were taught. Stone and city planning became the record, more enduring than ink or parchment. Similarly, in Mesoamerica, the placement of pyramids and observatories encoded calendars and solar alignments in ways that allowed continuity even in the absence of written documentation. This is not evidence of lost super-civilizations or mythical Atlantis. It is evidence of careful, long-term memory. Civilizations understood the impermanence of human life and the fragility of knowledge transmitted solely through words. Monumental architecture and standardization of units provided a continuity that spanned centuries, sometimes millennia. The Egyptians, for instance, maintained consistency in cubit measures across dynasties. Temples built thousands of years apart adhered to the same fundamental ratios and orientations. These practices suggest institutional memory encoded in culture, ritual, and material. Consider the continuity of astronomical observation. Egyptian priests maintained precise records of the heliacal rising of Sirius, guiding the timing of the Nile flood and agricultural cycles. Knowledge of stellar positions, lunar phases, and seasonal shifts was preserved not in libraries, which were limited and perishable, but in the very structure of monuments and ritual calendars. Each alignment and ratio acted as a ledger of accumulated observation. When a new generation assumed responsibility for construction or ritual, the inherited patterns ensured accuracy without reliance on fragile records. This form of memory was remarkably robust. In China, the precise orientation of ancient observatories along meridian lines allowed knowledge of celestial motion to persist across dynasties. In Europe, megalithic structures such as Stonehenge encoded solstitial and lunar cycles, allowing successive builders to preserve temporal understanding without written notation. Even in Polynesia, star charts etched into bark or memorized in oral form guided navigation across thousands of miles of ocean. Across cultures, humans developed the capacity to store and transmit critical information through physical, architectural, and performative systems. Sacred geometry, in particular, demonstrates how abstract knowledge could be encoded in repeatable forms. Ratios such as the golden mean, the square root of 2, or approximations of pi recur in temples, pyramids, and monuments around the world. These ratios could be reconstructed from proportion rather than measurement, allowing knowledge to survive changes in units, tools, or rulers. In this sense, knowledge was resilient not because it was hidden, but because it was expressed in forms inherently stable over time. A line etched in stone or a corner precisely aligned with the cardinal points could survive far longer than scrolls, which decay or are destroyed. The idea of long memory also helps explain the spread of architectural knowledge without necessitating direct contact. Independent cultures could arrive at similar geometric solutions because the forms themselves encode functional and observational truths. The square or circle is not merely symbolic, it is efficient, stable, and mathematically meaningful. Grid patterns in the Indus Valley, pyramid slopes in Egypt, and ceremonial alignments in Mesoamerica all demonstrate convergence in human reasoning and perception. These shared principles are transmitted culturally through apprenticeship, ritual, and standardized construction techniques. Knowledge is preserved not as abstract theory, but as practice that embeds itself into the material world. Even when civilizations fall, this long memory endures. Archaeological evidence shows that new cultures often inherit, adapt, or rebuild upon the structures of predecessors. Greek temples were influenced by Egyptian and Near Eastern prototypes. Roman engineers learned from Etruscan surveying and construction methods. Medieval cathedrals incorporated principles of proportion and orientation that echo ancient geometric understanding. In each case, the materiality of the knowledge, stone, brick, alignment, allows it to survive the collapse of institutions and the loss of written records. This continuity also extends to the intellectual approach. Civilizations understood that measurement, observation, and alignment are forms of communication across time. By encoding numerical and proportional relationships in physical forms, humans could ensure that knowledge survived generations without distortion. The Great Pyramid, the ziggurats of Mesopotamia, the observatories of Mesoamerica, and the temples of India all reflect this principle. They are more than monuments. They are enduring repositories of cumulative understanding, designed to transmit lessons long after the original builders have vanished. The concept challenges modern assumptions about linear progress. Knowledge is often imagined as cumulative and textual, dependent on libraries, books, and codified scholarship. Yet architecture and geometry reveal an alternative model. Knowledge can survive through practice, form, and proportion. Stone lasts longer than papyrus, rhythm endures longer than speech, and alignment persists longer than narrative. The durability of memory and material culture reshapes how we understand ancient intelligence, emphasizing continuity rather than mystery, persistence rather than accident. And so the question emerges, almost imperceptibly. If knowledge can survive through stone, through proportion, through repeated practice, then what might endure that we have yet to recognize? What lessons, embedded in geometry, orientation, or ratio, outlast ink and spoken word? The Great Pyramid, and monuments like it around the globe, stand as a testament to human ingenuity, not because they are perfect or mystical, but because they are deliberately designed to preserve understanding across the span of centuries. In this light, the term lost knowledge becomes misleading. The focus shifts to resilience, memory, and transmission. The builders were not operating under secret or mystical revelations, but through disciplined observation, ritualized practice, and careful encoding. They recognized that stone survives, that ratios endure, that geometry can speak across generations, and in doing so, they ensured that some truths persist far longer than the fragile lives of their creators. Books decay, scripts vanish, oral traditions fade. But a monument, a carefully measured and proportioned structure, can outlast dynasties. It can preserve ratios, alignments, and principles of observation that allow distant civilizations to engage centuries later with the same truths. The durability of knowledge in material form underscores a simple yet profound idea. Human understanding can be transmitted across time, not only through teaching but through design, practice, and the very language of proportion. Thus, when one stands before the Great Pyramid, it is not simply a relic of kings or a tomb. It is a repository of method, measurement, and memory. It embodies a continuity of thought that bridges generations, continents, and cultures. It prompts reflection on the endurance of knowledge. What survives longer, and why? And in this consideration, it quietly suggests that the human mind, through observation, replication, and material encoding, may preserve truths far more reliably than we ever imagined. Light has always occupied a space between the tangible and the transcendent. In ancient Egyptian cosmology, it was not merely illumination, but the first act of creation. Ra, the sun god, emerged from the primordial chaos, bringing order and life through radiance. Light was a principle of Ma'at, the cosmic balance, representing truth, harmony, and the cyclical rhythms of existence. Temples and obelisks were oriented to capture the solar journey across the sky, not merely for spectacle, but as a reflection of the eternal patterns that governed the heavens. The daily rise of the sun, the precise moment of its heliacal return, became both ritual and measurement, embedding astronomical observation into spiritual narrative. This intertwining of myth and observation is not unique to Egypt. Across cultures, light serves simultaneously as metaphor and metric. The concept of illumination, of clarity, of knowledge itself, emerges naturally alongside the physical phenomena that inspired it. In modern physics, light retains a dual character. It is both particle and wave, energy and information. Its speed, denoted as c, defines the structure of space-time itself. Einstein's theory of relativity establishes that the universe is constrained by this limit, linking energy, mass, and time into an inseparable fabric. In this sense, light functions as law, absolute, measurable, and unavoidable, yet it also carries the aura of symbolism. The Great Pyramid, in its proportions, alignments, and orientation, resonates with this duality. The numerical echo of the speed of light in its latitude suggests that what was once myth and ritual may also encode measurement and understanding. Perhaps Ra's radiance, celebrated in obelisks and solar temples, reflects a sophisticated awareness of the cycles and limits of the natural world. In this reading, symbolism is not merely metaphor, it is a form of empirical recording, a system of observation expressed in ritual, geometry, and placement. The abstraction of divine principle and the precision of measurable reality converge. Consider the king's chamber of the Great Pyramid, with its shafts aligned to circumpolar stars. Scholars such as Mark Lehner have noted that these alignments correspond to stellar positions that are stable over millennia. The Egyptians may have encoded knowledge of precession, celestial timing, and orientation within structures that also serve symbolic purposes. Light, whether in the sunrise illuminating the temple floor or in the observation of stellar paths, becomes both medium and message. The physical and the spiritual are inseparable. Observing the cosmos is itself an act of devotion, while devotion ensures careful observation. Modern physics provides another lens. The speed of light is foundational, appearing in Maxwell's equations, in the formulation of space-time intervals, and in energy-mass equivalence. It constrains the propagation of information, governs electromagnetic interactions, and underpins causality. For the ancients, the natural regularity of light, its daily rising and setting, its predictable paths across the sky, may have suggested an ordering principle, a universal constant in the fabric of reality. Symbol and law, once distinct, may in fact be intertwined, expressed differently across time, but arising from the same observation. This convergence raises a subtle but profound question. If human cultures embed measurement within myth, what counts as discovery, and what counts as narrative? Are the pyramids repositories of philosophy disguised as architecture, or of physics disguised as ritual? The evidence suggests that both interpretations are valid. Ratios, alignments, and dimensions preserve empirical truths, even as they express spiritual cosmology. Light, as myth, encodes the rhythms and limits of the natural world. As law, it defines the boundaries and possibilities of that world. Research in archaeoastronomy supports this synthesis. Studies by Anthony Aveni and Kate Spence have shown that pyramid orientation and temple placement were precise, often within minutes of arc relative to cardinal points. This precision implies methods of observation and calculation far beyond casual measurement. Alignments with solar solstices, heliacal risings, and circumpolar stars indicate that light and shadow were used as temporal and spatial markers, converting cosmic phenomena into humanly meaningful coordinates. Mythological narrative, then, may have served as both mnemonic device and framework for systematic observation. Acoustic studies further illustrate the interplay between physical law and symbolic design. The king's chamber exhibits resonance properties that amplify certain frequencies. Whether intentional or emergent, these acoustic effects highlight that architecture, like mythology, can preserve empirical phenomena. Light, sound, and proportion become interdependent channels through which observation and symbolism coexist. In this sense, Egyptian builders were simultaneously physicists, mathematicians, and ritualists, encoding knowledge in layers that operate on multiple registers. The philosophical weight is considerable. Science often divorces measurement from meaning, treating numbers and constants as abstract entities devoid of narrative. Myth, conversely, conveys values, cosmology, and understanding through story, metaphor, and ritual. At Giza, these approaches converge. Light is both the medium through which knowledge is apprehended and the principle that defines it. The symbolic framework ensures careful observation. The measurement framework ensures accuracy and repeatability. Neither can fully exist without the other, and yet the distinction remains subtle. Where does symbolic representation end and empirical measurement begin? Are the builders encoding light as a concept, as an observation, or as a principle later formalized in physics? The remarkable alignment of ratios, orientation, and proportionality suggests that these categories were not mutually exclusive for the ancients. They measured, they observed, and they encoded their understanding within systems that were simultaneously practical, philosophical, and spiritual. The persistence of this duality challenges modern assumptions about ancient knowledge. Light, for the Egyptians, was not merely a metaphysical metaphor, but a practical tool of observation. It structured time, informed architectural choices, and guided ritual. Today, physics treats light as law, immutable and measurable, The overlap is uncanny. By encoding observation within myth, civilizations may have preserved subtle empirical truths, providing modern science with clues that transcend cultural and temporal boundaries. As we consider the Great Pyramid, the obelisks and temples aligned to the sun, the question lingers. Did the Egyptians understand light as both symbol and law? Did their architectural and ritual choices embed measurement within narrative? Or is this a resonance that modern observers project backward, mapping physics onto mythology? The evidence suggests that such a strict separation is anachronistic. For the ancients, observation, measurement, and cosmology were intertwined. Myth, ritual, and architecture were conduits of knowledge, capturing the regularities of the cosmos in forms that could endure for millennia. Ultimately, the study of light at Giza forces us to reconsider the boundaries between science and philosophy, observation and symbolism. It hints that human perception, across time and culture, has the capacity to encode deep truths in ways that are simultaneously practical, aesthetic, and metaphysical. Light is law, yes, but also memory. It is structure, but also story. And in the monuments that endure, we find the convergence of these dimensions, inviting reflection on the continuity of human understanding and the subtle intelligence of civilizations that perceive the cosmos with both rigor and reverence. Where does symbolism end and measurement begin? At Giza, it seems they are inseparable. The Great Pyramid stands not merely as a tomb or monument to kings, but as something far more audacious, a point of interface. Its base touches the earth with precise alignment, while its apex points skyward, bridging terrestrial and celestial realms. Stone, laboriously quarried and arranged, becomes a medium through which human observation converses with the rhythms of the cosmos. The pyramid translates the tangible into the abstract, transforming cubic measurements, angles, and ratios into a language that speaks to forces far larger than human scale. In this framing, the pyramid is neither inert nor purely symbolic. It is a mechanism for encoding, transmitting, and preserving knowledge across dimensions of space, time, and cognition. Consider the alignment of the structure. The cardinal precision of the pyramid's sides is remarkable. Modern surveys place the deviation from true north at just a fraction of a degree. Scholars such as Kate Spence and Mark Lehner have reconstructed the likely observational methods, suggesting the use of circumpolar stars and careful sighting instruments. The result is not merely aesthetic, it is an encoding of Earth's orientation, celestial cycles, and geodetic relationships in 3 dimensions. In this sense, the pyramid acts as a translator. The geometry of stone expresses astronomical knowledge that could otherwise only be apprehended through long-term observation or complex calculation. Its proportions further reinforce this interface concept. Ratios embedded in the structure, including the relationship between height, base, and perimeter, can be read as reflections of fundamental constants. The link to pi in perimeter and height, and the potential correspondence to the speed of light via latitude, situate the pyramid within a network of mathematical, geodetic, and physical relations. These numbers are independent of units, surviving centuries of metric standardization and cultural shifts. As such, the pyramid becomes a persistent mediator between the measurable and the conceptual, a way to encode universal truths in enduring form. Yet the interface extends beyond numbers. The internal chambers, passages, and shafts suggest an awareness of both space and orientation, creating corridors where human presence, measurement, and celestial observation intersect. Shafts aimed at circumpolar stars may have functioned as sightlines, conduits for observation, or symbolic passages for the soul in Egyptian cosmology. Modern archaeoastronomy frames these alignments as careful, repeatable observation, demonstrating that the builders had sophisticated understanding of both local geography and celestial mechanics. Here, matter becomes interface, each stone a record of measurement and intentionality. The philosophical implications are profound. The pyramid connects human perception with universal structure, ratios, and alignments allow mortals to map the heavens, quantify the earth, and encode temporal cycles in stone. The builders may not have conceived of constants in the modern sense, yet their work engages the same universal relationships that contemporary physics describes. Earth, sky, number, and human ingenuity converge within a single structure, a tangible medium for relationships that transcend immediate utility or ritual. At the same time, caution must temper interpretation. The pyramid's function as an interface does not imply conscious encoding of modern scientific concepts. It does not mean the Egyptians anticipated Einstein or the definition of the meter. Rather, it suggests that through observation, measurement, and proportion, humans can encode patterns that resonate with fundamental aspects of reality. The pyramid becomes an enduring experiment, a system that translates empirical understanding of the world into a form that endures, interpretable by generations removed by centuries or millennia. The interface operates on multiple planes. On the terrestrial, it encodes local measurements, surveying accuracy, and geodetic proportions. On the celestial, it aligns with stars, solstices, and precessional cycles. On the conceptual, it bridges human cognition with abstract principles, converting ratios, angles, and alignments into a persistent record of understanding. In this sense, the pyramid functions as both instrument and archive, simultaneously measuring and preserving knowledge, translating reality into form, and form back into reality. One of the most striking aspects of this framing is the implied audience. If the pyramid is an interface, it raises the question, for whom was it constructed? The Egyptians themselves may have benefited from its practical, ritual, and mnemonic functions. Priests and surveyors could interpret alignments to schedule rituals, mark seasons, and maintain consistency across projects. Yet the structure also speaks to the future, to generations of observers who would decode the same ratios, alignments, and patterns. The pyramid, in this sense, is both tool and message, an enduring medium through which the universe and human understanding intersect. The interface metaphor also extends to temporal perception. Stone is durable. It preserves ratios, alignments, and orientations far longer than papyrus or spoken word. In encoding knowledge into architecture, the builders created a medium that interacts with time itself. Each generation that observes the pyramid encounters the same proportional relationships, the same geometric language, the same astronomical markers. Knowledge becomes tangible, measurable, and repeatable across centuries. The structure mediates not only space but also temporality, connecting observers separated by thousands of years through shared measurement and observation. Ultimately, the Great Pyramid can be seen as a point of convergence: Earth, sky, number, and human consciousness. It is neither passive nor purely symbolic. It is a medium, a translator, and a repository. Its stones encode measurements that reflect geodetic awareness, astronomical observation, and proportional reasoning. Its alignment bridges terrestrial and celestial frames. Its ratios resonate with universal constants, and its enduring presence challenges assumptions about how knowledge is preserved, communicated, and accessed across time. The final question emerges naturally. If the pyramid functions as an interface, as a medium connecting matter and number, human and cosmos, who was it intended for? Was it for the priesthood, for the king, for future generations of observers, or for some understanding yet beyond our grasp? The answer remains elusive, but the idea reframes the monument entirely, not simply a tomb, not merely a marvel of engineering, but a bridge between worlds, a dialogue etched in stone between humanity and the universe itself. For millennia, the Great Pyramid has stood as a testament to human ambition, skill, and observation. Yet as we trace its alignments, ratios, and celestial correspondences, a stark truth emerges. We cannot know the builder's intent. No inscription declares we encode the speed of light. No papyrus records an exact methodology for mapping the Earth in cubits and star cycles. The evidence is compelling, suggestive, even uncanny, but definitive proof remains elusive. Science can measure, compare, and reconstruct. History can contextualize and speculate. But the final answer slips beyond reach, a shadow always at the edge of understanding. This confrontation with uncertainty is not weakness. It is the heart of inquiry. Precision matters, whether in the careful orientation of the pyramid to true north, or in the measurement of its base and height to the nearest fraction of a cubit. The ratios embedded in stone endure for thousands of years, independent of human memory or documentation. The latitude of 29.9792458 degrees may echo the speed of light, or it may not. Either way, the alignment exists, the precision persists, and the questions demand contemplation. The monument itself forces us to grapple with limits, the limits of our measurement, our reconstruction, and our imagination. Mystery in this sense is not ignorance. It is a space for engagement, for reflection, for the recognition that the universe and its human interpreters are intertwined in ways that defy simple categorization. To accept uncertainty is to honor the evidence without overstating it, to marvel at the correlations without claiming omniscience, to allow wonder to coexist with skepticism. It is to acknowledge that some aspects of knowledge are relational, emergent, and dependent on context. This stage is also emotional. There is a peculiar tension in standing before the pyramid, knowing that calculations align with modern constants, knowing that architectural ratios echo principles discovered millennia later, and yet realizing that no record confirms intention. It is a confrontation with our desire for certainty, for linear explanation, for closure. But the pyramid resists such neatness. Its enduring presence reminds us that human curiosity, observation, and ingenuity can produce results that transcend immediate understanding. In this ordeal, the mind begins to shift. The drive for absolute answers softens, replaced by an appreciation for the persistent questions themselves. The precise measurements, the alignments with stars, the proportional relationships, all become invitations rather than solutions. They are the markers of intelligence reaching across time, and their significance may be forever, just beyond full comprehension. And so the realization crystallizes. Certainty may be the true illusion. The allure of final answers tempts, yet the pyramid demonstrates that the richness lies in exploration, in the questions that persist, and in the subtle dance between measurement, observation, and interpretation. To accept uncertainty is to step closer to the essence of inquiry itself, where mystery is not a deficit, but a dimension of understanding, and where the Great Pyramid continues to speak across millennia, asking only that we listen with both rigor and humility. The Great Pyramid did not know the speed of light. It could not, and it need not. Its stones carry no consciousness, no intent to encode modern physics. What they do embody is an extraordinary understanding of measurement, proportion, and observation. By translating the world into ratios, alignments, and geometry, the builders created a system capable of capturing truths about their reality with astonishing precision. In doing so, they produced a monument that continues to communicate across millennia, a silent testament to human curiosity and ingenuity. This perspective transforms the way we view both the pyramid and ourselves. The structure is not a cryptic message from an advanced civilization or a mystical artifact of lost knowledge. It is evidence that humans, even 4,500 years ago, were capable of extraordinary observation and abstraction. By encoding proportions that reflect universal relationships, the builders became early participants in the measurement of reality, translating the natural world into forms that endure. They remind us that discovery is often a process of noticing, recording, and refining patterns inherent in the environment, rather than inventing them from nothing. In this reframing, humanity is the rediscoverer, not the inventor. The constants and ratios embedded in stone were always present in the cosmos. The pyramid merely mirrors them, capturing the world's structure in a tangible form. When modern scientists observe these correlations, they are not uncovering secrets hidden for millennia. They are recognizing patterns that the ancients intuited, patterns that reflect the consistent, measurable laws of nature. In this sense, every measurement, every observation, every equation is part of a long continuum of human engagement with the universe. The lesson is profound. Knowledge is not solely the product of instruments or calculations, but of attentive observation, careful replication, and the willingness to encode what is seen into enduring forms. The pyramid teaches that the act of measuring reality can itself produce results that transcend time. Its architecture, proportions, and alignments are not relics to be decoded as puzzles, but living testimonies to human perception, reasoning, and the persistent drive to understand the world. And yet the story does not end here. The Earth itself continues to speak, through mountains, rivers, coastlines, and the subtle rhythms of celestial motion. If the pyramid can preserve understanding across millennia, what other truths lie waiting in plain sight, encoded in the patterns of the planet, the cycles of the sky, or the ratios of life itself? The monument calls us not merely to look backward, but to remain attentive, to continue observing, measuring, and listening. It is an invitation to rediscover the cosmos, one precise alignment, one enduring ratio at a time. What else is Earth still telling us? If we step back from measurement, from theory, from speculation, the Great Pyramid remains. Its stones endure, silent yet precise, aligned and proportioned in ways that speak across millennia. No inscription reveals intent. No manuscript confirms understanding. Yet ratios persist, alignments endure. The structure continues to reflect the cosmos in its own language, a language built of observation, geometry, and enduring human attention. We may calculate, we may compare, we may theorize, we may marvel at the coincidences, the harmonies, the echoes of constants that govern space, time, and light. But none of this provides certainty. The pyramid does not answer. It invites, it suggests, it mirrors. Its endurance is a form of knowledge in itself, but one that resists conclusion. Perhaps the most profound realization is not in the numbers or the alignments, but in their persistence. Millennia of sunrises and sunsets, stars rising and setting, generations passing, all leave the pyramid unchanged, holding patterns that humans can interpret, measure, and reflect upon. The deeper we look, the more questions emerge, and the more the boundary between past and present, observation and understanding begins to blur. We are left, finally, not with proof, not with belief, but with awareness. A monument standing quietly in the desert, a reflection of human curiosity and the cosmos alike. Its message is not declarative, it does not demand agreement, it simply exists as a mirror, waiting for attention, willing to be read without ever giving all its secrets. And so the question remains, lingering as a thought, as a challenge, as an invitation to continue observing, measuring, and wondering. If ancient stone can still mirror the deepest laws of the universe, what does that say about how old our understanding truly is? Thank you for joining us on this extraordinary journey through the universe on frontiers of infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.